In this video, I'm going to wrap up our discussion on the Schrodinger equation solutions for an infinite rectangular potential well. And so the first thing I wanted to sort of quick talk about was the momentum of of a particle in our infinite rectangular well. So this is the momentum, and this is what you would get if you used a momentum operator. But we know that the momentum is related to the position by the Fourier transform. And so this right here is the Fourier transform. Remember, this right here is our wave function as a function of space. Then this here is the Fourier transform, with this just being a normalization factor. And so we're taking the Fourier transform of this wave function, which in position space we saw had shapes like this depending on what this n is. But then if we do the Fourier transform, or if we took the wave function and acted on it with a momentum operator, we would get things like this. And so this is in momentum space. So over here we saw what the probability, well, these are the probability amplitudes. If we squared them, they would be probability, they would just be probabilities. But you can imagine the probability of n equals 1 is going to have a similar shape, where with n equal to it'll have a similar shape, but this part will become positive there. And so the shapes will be kind of similar. They will just all be positive rather than going going into the negative like that. But anyway, this is the probability in momentum space. And so we can see, for instance, when n equals 1, so when we're at this lowest level here, at the ground state, then we have most of our momentum is 0. But you can see that this is a distribution, so there is some momentum that is non-zero. And then, well, we can see here that we go from negative to positive, and negative momentum just means essentially that it's moving in the opposite direction. So if we defined the positive direction as this way, then positive momentum would mean that it's moving that way, and negative momentum would mean that it's moving that way. And so we see that as we go up in energy levels, our momentum is also increasing in magnitude. We see that it's going more positive, but also more negative, which, as I said, just means the momentum, but moving in the other direction. And so we can see here that as our n gets higher and higher, our momentum is becoming larger and larger in magnitude. And so I'm not going to solve this this right here, because it's really not that informative to see what the solution to this is. I think it's more informative to just sort of look at what the graphical representation of the solutions. If you're interested in the solution, then that student's guide to the student's guide to the Schrodinger equation is where I got all of this from, and it does show the solution to this. But these are all pictures I just took on my phone right out of that book, which I will link to in the description. And then, so changing gears a little bit, so I talked about before that our wave function, it can be it is a a linear combination of a bunch of different wave functions. So we can have this, I guess, will probably be a lowercase phi, or so I think that looks something like this. Often looks something like this. But anyway, so and there should be a Cn here. But I said that these are a linear combination of these. Um, and so when we take a linear combination of them, we have to actually bring back the time term. So we've been using the time independent. I'll even capitalize it. Time independent uh, Schrodinger equation, which I'll just write as SE. But if we if we have sort of a pure state, I guess you could say, where it's just purely n equals one, there is no contribution from any of the other energy levels, then we would have a time independent state, and it would just sort of sit there as a probability distribution like this. But when we start combining them into these linear combinations, then we have to bring in the time dependence, because now there is sort of an evolution happening between between, say, n equals 1 and n equals 2, for instance. And so to do that we have to bring back the time term, which was this, for instance, and this. And so this is looking at so this is a linear combination of state 1 of n equals 1 and n equals 2. That's why this doesn't have a number here, and this has a 2 here. And so the A and B here are sort of I guess you could say, the Cn in our linear combination up here. So that is the contribution of each of these. So this is just looking at a linear combination of two states, the one state, the n equals 1, and the n equals 2 states. And so if we want to put A as 0.96, which is what it shows here, and then B will be 0.28, because if you take A squared plus B squared, that has to equal 1. If it's just A plus B, that doesn't necessarily have to equal 1. And so if we take the square root of these things, then that's where we get this 0.96 and 0.28. But the takeaway here is, and like I said, well, I didn't say it about this yet, but in the book that I'm going from, the Student's Guide by Daniel A. Fleisch, the Student's Guide to the Schrodinger Equation, it goes through a lot more of the mathematics and shows the normalization of these and all that kind of stuff. But I just kind of wanted to focus here on the takeaway message, and that is, if we have a contribution of 0.96 from the n equals 1 and 0.28 from the n equals 2, then we see that the shape of this changes over time. So at t equals 0, we have a probability distribution that looks like this. At t equals 1/7 time, then it changes a little bit like this, and at 2/7 it's like this, and you can just see that this is just kind of wiggling back and forth, and so that is when we have more contribution from n equals 1 than from n equals 2. If we have equal contribution, then we actually get shapes that look more like this, where we have this large lobe here and a small one here. Then you see that it's I guess the probability is sort of moving over to this side, and we end up getting something that looks like this, and then it kind of moves back over to the other side, and we get this sort of oscillation back and forth if we have an equal mixture of the n equals 1 and n equals 2. And you can imagine, if we start adding in more of these, if we start having for instance, like C1 phi 1 plus C2 phi, or psi 2 plus C3 psi 3, that's going to have an even different evolution in time. Then if we add in even more, uh, oops, then we will get even different looking evolutions over time. But the takeaway message is that if we are looking at just a single energy state here, then we can use the time independent Schrodinger equation because this is not going to change. But if we start having linear combinations of them, or superpositions, if you will, then we will have that time dependence. It will evolve in time. And so we can actually look at, well, this just describes what is causing the time evolution. And so this is the probability here. And so that is if we have our psi is equal to I guess you could say psi 1 plus psi 2, and we want to get the probability, which is psi the complex conjugate multiplied by psi, which would be the psi 1 plus psi 2 complex conjugate times psi 1 plus psi 2. And so that's what this is doing here. It's just showing the wave functions explicitly here. So this, for instance, is the well, this is actually after foiling. So this right here is the psi 1 times psi 1. This is the psi 2 times psi 2 here. Then these are the cross terms here. And you can see that this right here and this right here do not have time dependence, but these cross terms do have time dependence given by this here and this here. And so we can actually take these two cross terms and sort of, well, we just factor out the the sine times sine, or the sine with n equals 1 times sine where n equals 2, and factor that out so that we end up with this term right here, which then can be, we can use the identity, sort of the identity of cosine, and that gives us this right here. So we see there's equal signs here and here, so it's this, we factored out the sine where n equals 1 and sine where n equals 2, giving us this, and then that equals this, where we just sort of use the identity, the Euler identity, to change that into this cosine term here. And that has the time dependence with the change in energy levels. And what this is doing is actually telling us that there is a phase evolution or phase change in time. And so that's why we end up having these different shapes over here, is because the phase of the n equals 1 and n equals 2 is changing over time. And so that is through the constructive interference of the two states. Well, the constructive interference is changing because, say, we have that plus that, then as the phase changes, we would have that plus perhaps that. And so that's why we are going to end up having the lobes sort of changing. So if this is the state of both of them at t equals 1, and then this is at t equals 2, we see that as the phase changes, then the constructive interference of these is going to change. And that's what this cosine term here is doing, is telling us the phase evolution in time. And so down here, so this is telling us the angular frequency here, and so this is just looking at the inner term, or the argument of the cosine here. And so using the energy levels, we can then use, so E2 minus E1, we're going to have this, the n equals 2 minus the n equals 1 here, and that will give us, so 2 squared is 4 and 1 squared is 1, so that gives us 3. So this tells us the energy here, or the energy difference between them right here, or I guess the frequency difference between them right here. But the idea, the takeaway message is that it's just this phase evolution. So when we use the time-dependent Schrodinger equation, uh, which we have to do when we are using linear combinations of these states, then we have this change in phase, this phase evolution that causes the change in shape of our probability distribution, which we can see in these figures right here, which come out of that book, The Student's Guide to the Schrodinger Equation. But anyway, that I think wraps up what I wanted to talk about with the infinite rectangular well of or potential well rather. In the next couple of videos, I'm going to talk about the finite well, which well, the main difference, I guess, I'll just give a little spoiler here. If we have the infinite rectangular well here, then we know that that our wave function has to be 0 at both edges. Whereas if it's finite, then we can actually have it be not 0 at the edges, and we actually can have it go outside of the rectangular well. And so we will see in the next few videos that sort of the main thing here is worrying about these boundary conditions, because these have to be continuous here. So we're going to have a function that tells us what is going on where the potential is 0, and then different functions telling us what's going on when the potential is finite but greater than 0. And so that's sort of the biggest difference between the infinite and the finite rectangular wells, is just worrying about is how we handle these boundary conditions here, and the fact that we can have non-zero wave function within the potential. And I think sort of the analogy that I used in the previous video is if we have sort of an infinite square well or infinite rectangular well of potential, we can think about it like a box that we have some object in. We have some mass inside here. And no matter how much energy you hit this with, and it bounces around inside here, it's never going to be able to come outside of this box. Whereas if it's finite and we have a mass in here, we can give it some energy that will actually allow it to come outside here. This analogy is not perfect because this is a probability distribution rather than some classical sort of object here coming outside of a box. But I think that's just sort of a rough analogy to sort of think about why if there's an infinite potential, we could have to be 0 at the edges and there can't be any wave function outside of it. Whereas when it's finite, we do not have to be 0 at the boundaries here, and there can be wave function outside of it. But anyway, let's not get too ahead of ourselves here. I hope this this little 3-part series on the infinite rectangular potential well was enlightening to you, and I will see you in the next video.